Okay, so we are currently going to start a short video where we cover a topic in this lecture 1 from week 12, which was Introduction to Numerical Integration. And so if I go ahead and I open up the slides, then I say slides, but I mean notes, and we scroll down, we get down here to a thing called Simpson's rule and also trapezoidal rule. And so what this video is going to do is going to briefly show you how these things work, but by hand. If you can do them by hand, it'll be easy to code them up. So with that said, let's go ahead and get started. So let's suppose, example, let's take a relatively simple function here. So I'm going to let f of x. Actually, I don't want to say it that way. Let's say this. So problem 1, we will use Simpson's rule. Nope, trapezoidal rule first. Trapezoidal rule with, let's say, n equals, let's say, 4 subdivisions, we could say, to estimate, and then we need an integral. So we'll have an integral, and we need 4 subdivisions needs to be sufficient. So let's go ahead and say we're going to integrate from 0 to 2, and we need a function, and we're going to make this function relatively simple because the function is not really the point. So there we go. Now, of course, we know that you could easily calculate this actual area, right? Because we could draw a picture, and 1 over x squared, of course, looks like this on the positive side. As soon as I do this, I realize that we don't want to go from 0 to 2. So let's go ahead and change this. Let's call this 1 to 3 instead. So let's go ahead and put 1 here, and then 2 here, and then 3 here. And we know that what we're trying to calculate then is this area right here. And of course you can do that by hand without numerical integration, because you would just say integral from 1 to 3 of x to the minus 2 dx. So what do you got to do? You got to add 1 to the exponent, and then you have to divide by the exponent, and then we need to go from 1 to 3. So you plug in a 3, you get negative 1 over 3 minus, and then you have plug in a 1, and you have negative 1 over 1. So what do you get when you look at this all together? You get 1 minus 1/3, which is, I guess, 2/3. Hopefully I did that right. I teach computer science now. Been a while since I taught calculus. But let's go ahead and try to do this now with the trapezoidal rule. So looking at the trapezoidal rule, you can see it, over here. And what we would do is this. So now try trapezoidal rule. Now, we did something very similar to this in class, but we didn't do trapezoidal rule. I think we did midpoint rule, left-hand rule, those kinds of things. So the way that trapezoidal rule would work is very similar to the left-hand rule or the right-hand rule. So the first thing that you would do is we would calculate delta x. So the delta x, which is going to be the spacing for our rectangles, although in this case they're trapezoids, would be b minus a over n. So for this specific example, of course, we're going to get the the a and the b are going to be the limits of integration. I probably should be pointing at the integral here. The a and the b are the limits of integration, and we also have n equals 4 for the number of subdivisions. So that would be, in this case, 4 minus 0. No. The limits of integration are 3 and 1. I don't know what I'm saying. And then the n is 4. So you'd get 3 minus 1, which is 2, over 4. So, of course, we end up with 0.5. And then after you get the delta x, we would compute some y values. Sorry, x values. And so the x values are going to start at a. So the x0 would be a, which is just 1. And then from there, you add delta x every time. So the x1, you would add delta x to the 1, and we'd get 1.5. And then for x2, you would add another delta x. So you'd add another 0.5, and you get 2.0. And then x3, you would add another 0.5. So you get 2.5. For x4, you'd add another 0.5. So you get 3.0. And then that's where you would stop, because that happens to be b. So we're integrating from 1 to 3. And of course, we see that we are indeed starting at 1, and we are going to end up at 3. Okay, so we calculate these x values. Now, at that point, we can go to our trapezoidal rule. You can see it to the left here, but specifically, the trapezoidal rule estimate would be, I guess I'll call it T4, just copying the notation, and it would be delta x over 2, and then in parentheses here, we would have f of, we'll write it out, x0 plus 2f of x1 plus 2 f of x2, I'm out of space, plus 2 f of x3, and then when you get to the last point, the x4, it would be just f of x4. And so that matches up with the formula that you can see right here next to this on the left. And then at that point, we would basically just need to fill in the values. So the T4, I selected the wrong thing there. The T4 would be delta x, which is 0.5 over 2. And then f of x0, right? Of course, x0 is 1. And so it'd be f of 1 plus 2 f of 1.5 plus 2 f of 2 plus 2 f of 2.5 out of space, and then plus f of 3. And you want to note that they all have coefficients of 2, except for the first value and the last value. I didn't, where's the pointer? There? Is that it? Yeah. So this one right here has a coefficient of 1, and the one at the end has a coefficient of 1, but it's 2 and 2 and 2 in the middle, and that's what the formula for the trapezoidal rule says. So our function here was 1 over x squared, right? So we have right here is our f, 1 over x squared. So if you were to plug these numbers all in, we would get that this is 0.5 over 2, which is 0.25. And then f of 1 is 1 over 1 squared. And then you have 2f of 1.5 is 2 over 1.5 squared. And then 2 over 2 squared. And then 2 over 2.5 squared. And then finally, 1 over 3 squared. So we would have to punch that into a calculator or something. So I will use like Wolfram Alpha if I can. Actually having trouble doing this on an iPad. Let me see. Wolfram Alpha. All right. Oh, now the keyboard pops up. So what do we have here? What do we need to type in? We need to type in this. So 0.25 times, and we've got 1 over 1, which is 1, plus 2 over 1.5 squared, plus 2 over, actually that's just 2 squared, so 2 over 4, plus 2 over 2.5 squared, plus 1 over 3 squared, which of course is 1 over 9. And then we can throw some parentheses on there, and we get, hopefully, 0.705. So that should be relatively close to the actual value, and that's what we get. Okay? Now, having said that, the key to doing the trapezoidal rule properly, right? I feel like the step 1 here was relatively simple. Right, this was relatively simple here. Calculating the x values is relatively simple. Writing out the trapezoidal rule, you just need to remember that only like the first point and the last point have a coefficient of 1 in here, and the rest have coefficients of 2. And that's just simply from the trapezoidal rule. Now, having said all that, it's really important that you understand trapezoidal rule this way, because Simpson's rule is very similar. The only difference with Simpson's rule and trapezoidal rule, well, I mean, not the only difference, but the big difference is when you get to the point of writing out the equivalent of this step right here, you can see in the formula, in the Simpson's rule formula, that the first number, right, the f of x0 has a coefficient of 1, and you can see that the last number also has a coefficient of 1, but then you see this kind of business where it says there's like a 4 there, and then there's a 2 there, and you're going to see 4s and 2s in the formula. And so that's kind of the key. So let me just write a little bit here, maybe pick a different color. Yeah, that's fine. So in trapezoidal rule, it was like delta x over 2, and then it's like f of x0 plus 2 f of x1 plus 2 f of x2 plus dot dot dot, right? And you keep going, and when you get close to the end, you still have 2 f of, let's say, x in minus 1, but then the very last one has a coefficient of 1. Now, I'm making a big deal out of that, but that's the key, because when you do the Simpson's rule approximation, it starts out delta x over 3, first of all, but then what happens to the numbers in between is you start out with f of x0, which, you know, of course, is exactly the same, but then after that one, you are going to alternate 2s and 4s. Okay, so you're going to go 4 f of x1, and then 2 f of x2, right? So you have a 4, and then you have a 2. And then this continues on. So the next one would be 4 f of x3, and then you'd have 2 f of x4 plus dot dot dot. You keep alternating 4s and 2s. So it's 4, 2, 4, 2, etc. You do that all the way till you're getting almost all the way to the end, but then when you do get to the end, you need to make sure that the pattern works out to end with a 4, and then that would be your f of x in minus 1, and then finally you finish with a f of x in. So I'm out of space, but that's where it ends. And so you just have to understand this pattern of 4, oops, that's not what I wanted. Where's undo? There it is. You have to understand this pattern of 4, then 2, then 4, then 2. And when you get to the end, it'll be a 4, that you end with before you get to the last entry. That's hard to read, so let's just delete those. Now, I said that a few times, like, how do we end with a 4 for that pattern? Well, if you look at Simpson's rule carefully, it will tell you that it says that the rule requires n to be an even number. That's what will make that happen. So it just happens if n is even. Okay, so with that said, let's see if we can now work out Simpson's rule for that same integral. So we're going to do the same exact problem. Let me pick a better color. So example, let's just do integral from 1 to 3, same 1 over x squared dx. And we're going to use Simpson's rule with n equals 4. Okay, so it starts out exactly the same way. So our first step here is going to be to compute the delta x. So you end up with delta x, same thing, b minus a over n. So 3 minus 1 over 4, so 0.5. Exactly the same as before. The next thing is we need to compute the x values. And again, that's also exactly the same as before. So your first x value is 1 because we're going from 1 to 3. And then from now on, you just add delta x until you get to the b eventually. There we go. Right? And you can notice that the n here is 4, which is even. Right? So we needed this even in order to even be doing Simpson's rule. And then now we can try to compute Simpson's rule. So use Simpson's rule. So what do we have? Well, we'll say S4 for Simpson's rule with 4 intervals. It is delta x over 3. And then the pattern is f of x0 plus, and now we have to remember the pattern, which alternates 4 and 2. So it's 4 f of x1 plus 2 f of x2 plus 4 f of x3, and then the last one is x4, and so we'll have plus f of x4, which I'm kind of out of space again. So there you go. And so again, the pattern here starts with the 4, and it goes 4, 2, 4, and that's as many, as we have. So the first entry has a coefficient of 1, last entry has a coefficient of 1, and then in between it's 4, 2, 4. Okay, so when you go ahead and work this out, then the delta x was 0.5 over 3, and then in here you have f of x0, which was 1 over 1 squared, and then 4 f of x1. x1 is 1.5, so that's 4 over 1.5 squared. And then 2f of x2, that's going to be 2 over 2 squared. And then 4 f of x3, so that's 4 over 2.5 squared. And then finally, f of x4, which is going to be coefficient of 1, so 1 over 3 squared. So what is that? Well, you got to work that out. So we can maybe we can just edit this. Maybe, I don't know. Let's see, we'll try. Well, not if I can't move the cursor over because I don't know how to use an iPad. Please? No? No, it just doesn't do that, huh? Just can't. Okay. You know what? I give up. Close it. Or where's the keyboard? Give me the keyboard. No, please just give me a keyboard so I can type. All right, you know what? No keyboard, so I think I can use a regular keyboard. Wish me luck. Okay, what are we trying to do? So we're trying to type in this down here. So we have 0.5 over 3 times, and then we have 1 over 1 squared, which is 1, plus 4 over 1.5 squared, plus 2 over 2 squared, so that's 2 over 4, which is a half, plus 4 over 2.5 squared, and then plus 1 over 3 squared, which is 1/9 again. And we do that, and we get 0.67. Sorry if that was loud, I was closing the keyboard. So then we have 0.67148. So that's our approximation. And so we should remember that the original, that our correct answer was 2/3. And so you can see that the trapezoidal rule, which was one of our best methods before now, came up with 0.704, which is pretty close to 0.67, right? It's only off by 0.03 basically. But if you scroll down here, right, the Simpson's rule with the same number of intervals is 0.67. So that is even closer, right? So that's actually very close to the right answer with only 4 subdivisions. So Simpson's rule is very good. And I just wanted to illustrate this with one worked out example so that you could see the pattern that goes 1 and then 4, 2, 4, and that alternates, that 4, 2, 4 pattern. And so that's going to be slightly harder to code than some of the other methods, but you can use a for loop for that. Rather than trying to do MATLAB vector code in order to code up Simpson's rule, you could just use a for loop that just loops through the x values and adds them up. That's kind of my recommendation. But yeah, so you could do that. And why would you need to do that? Well, if you look at, go back, please. No? Okay. Because if you look at the homework 6 here, one of these has you using Simpson's rule. So we wanted to try to compare Simpson's rule. Actually, part 2, implement Simpson's rule. And then you want to try to compare midpoint rule, trapezoidal rule, and Simpson's rule with 6, 20, and 100 subdivisions here. And so the Simpson's rule code is the only code that you don't really have from the lab last week. But yeah, so you can talk to me if you have trouble implementing Simpson's rule, and we'll work through it. And other than that, I think that's about all I have to say here. So hopefully this is useful to somebody, and hopefully the audio actually recorded. And with that said, I'm going to go ahead and end this now.